How could a universe governed entirely by the laws of physics and chemistry ever give rise to life? An autocell is a new model for a possible transitional form between non-life and life. It's a simple molecular system that could emerge spontaneously in a pre-life universe, a universe devoid of any life form or intelligence to induce its creation. An autocell is the product of the spontaneous coupling of two common, well-understood chemical processes. One of the processes is called autocatalysis, in effect a chain reaction in which certain molecular reactions occur at an accelerating rate until reactive molecules are depleted. The other process is encapsulation, whereby larger molecules spontaneously form tubes or spheres that temporarily enclose upon and preserve other molecules in close proximity to each other. Autocatalysis and encapsulation have each been implicated in origins of life scenarios, but neither process by itself has proven to be the key. Autocatalytic cycles dissipate when they run out of molecules to transform. Molecular capsules eventually break up and their contents also simply dissipate. With autocells, however, the autocatalytic and encapsulation processes interact with each other, becoming mutually supporting. Autocatalysis produces encapsulation molecules. Encapsulation keeps the autocatalytic molecules from dissipating. Here's how they work. First, a little background. Molecules are made up of atoms that form strong bonds with each other. A molecule's effective shape is the product of how and where the bonds between atoms form. In this color-coded animation, we see two molecule types, purple and red, and the atomic structures that give them their shapes. If red and purple molecules happen to bump into each other from a certain direction, they might bond. They bond more readily in the presence of a catalytic molecule, such as the one depicted here in green. The catalyst acts like a mold, bonding loosely with one of the two, in effect holding it in a position that facilitates bonding with the other molecule should it eventually happen by. The bond between the two is stronger than the bond between either and the green, so they end up breaking off together, leaving the green molecule available to facilitate another bond. The green molecule is therefore a catalyst, a molecule that facilitates a reaction without itself being changed by it. These green molecules are themselves the product of two smaller molecules bonding to each other, a reaction that could occur spontaneously by a chance encounter between blue and yellow molecules, but is more likely to occur in the presence of a catalyst like this magenta one. In our depiction, magenta molecules are catalyzed by green molecules, and green molecules are catalyzed by magenta molecules. This is a simple depiction of an autocatalytic cycle, a relationship of mutual facilitation between two or more species of catalytic molecules. With each cycle of mutual formation, more catalysts are produced. By a compound interest-like effect, therefore, autocatalysis becomes a chain reaction where more catalysts producing more catalysts. The cycles would continue to accelerate until any or all of the transformable molecules, yellow, blue, red, and purple, are locally depleted. Typically, autocatalysis involves more than two species of catalytic molecules. We depict it here with two for simplicity. Autocatalytic cycles often produce byproducts, molecules produced by the cycle's progress that do not themselves contribute to it. Here we depict not a byproduct, but a secondary feature of one of the catalytic molecules. In addition to serving as catalysts, the larger flat green molecules form shells or spheres, as do many common molecules. As these shells form from the products of the autocatalytic cycle, they are likely to occasionally capture a few members of the autocatalytic cycle. In closed encapsulation, the autocatalytic cycle would run out of transformable molecules, but these encapsulations could become, in effect, autocatalytic cycle starter kits. Should one happen to open in the presence of transformable molecules, the autocatalytic cycle would start again, creating more catalysts and indeed more encapsulations. Autocells would therefore be self-reconstituting. They would alternate between an enclosed seed-like state and a broken open growth-like state. Depending on where and when they were opened or closed, a population of autocell lineages would be subject to differential survival. Real-world autocells would be more complex than those depicted in these simple illustrations, with autocatalytic sites involving many more molecular types, some interchangeably. Lineages of self-reconstituting autocells would acquire varied characteristics. While autocells would not be defined as living, they nonetheless would possess some of the features that begin to distinguish life from non-life and could be the simplest evolvable units